Good evening. I am Somaabha Bhattacharjee, third year Petroleum Engineering Undergraduate from RGIPT Institute of Petroleum Technology, JEF, India. And today I'm going to present on the topic carbon capture, utilization and storage. Now let us discuss what will be covered in today's presentation. First, we'll start with the basic introduction of the CCUS. Then we'll move on to a few terminologies which include the carbon inventory and the carbon cycle. Then we'll discuss the various stages of the CCUS process, which involve the carbon capture process, the transport process, the storage process. Then we'll also discuss the various zero emission power generation concepts. Then we'll move on the fourth stage of the CCUS process, which is the carbon utilization. And then in the end, we'll discuss the different policies in various countries across the globe. Now let's get started with the presentation. So first, let us start with the basic introduction of the CCUS. So basically, CCUS stands for Carbon Capture, Utilization and Storage. So it is a technology which involves four basic steps, which are capture, transport, storage, and use. So talking about capture, so the first step is that we capture carbon dioxide from the fossil or the biomass fuel power stations, industry facilities, or we can also directly capture the carbon dioxide from the air. Now the second process is transport. In this, we transport the compressed carbon dioxide which was captured earlier. We transport it either by using ship or through pipelines from the point of capture to the point of usage or storage. Now talking about storage, so it means that we permanently store the carbon dioxide either in geological formations, which may involve underground salt aquifers or maybe depleted oil and gas reservoirs, or it can also be onshore or offshore storage facilities. Now talking about the fourth and the final step, which involves use. In this, we use the captured carbon dioxide as an input or feedstock to create valuable products or services. Now let us see the various different CCUS projects around the world. In this world map, we can see that the blue circles represent the industry of fuel transformation and the green ones here represent a power sector. So as we can see that majority of the CCUS facilities are concentrated in this North American region, and in the other continents, very few like one or two are present in all the different continents. Now this is a graph which shows the CCUS facilities in operation by application from the year 1980, and with a gradual increase of 10 years like 1980, 1990, 2000, 2010 and 2021. So as we can see that there is a gradual increase in the use of CCUS facilities as we move from 1980 to the year 2021. Now we have discussed the introduction. Now we should know about a few terminologies before focusing on what is the CCUS actually. So let us discuss about first one is carbon inventory. So carbon inventory records the amount and the sources of carbon dioxide, CO2, and other greenhouse gases that are released in the atmosphere due to various processes such as burning fossil fuels and other such activities. So there are four main contributors to this carbon inventory, which include the carbon inventory due to atmosphere. Then we have biosphere, lithosphere, and in the end we have carbon inventory due to ocean. Now let us discuss all the carbon inventories one by one. So first we have carbon inventory of atmosphere. So in this we can see that the total inventory of carbon dioxide present in the atmosphere is approximately around 3200 gigatons of carbon, and there is an annual increase of 3.5 gigatons of carbon per year. So in this table, as we can see that carbon dioxide (CO2) contributes 2300 gigatons of carbon out of the 3200 in total, which is approximately around 72%, and the remaining contributions are made by atmospheric carbon, made by the methane, that is CH4, nitrous oxide, N2O, and with very few traces of carbon monoxide, CO, and chlorofluorocarbons, that are CFCs, and all these components total to 3200 gigatons of carbon, that is the carbon inventory present in the atmosphere. Now let's move forward. Now we have carbon inventory of biosphere and soil. So the terrestrial carbon inventory holds 2200 gigatons of carbon, with 600 gigatons as living biomass and 1600 gigatons as the organic carbon in soil and sediment. So in this table, as we can see, these are the various components. These are the various components. They are plant and animal detritus, the modified soil carbon, inert carbon, and then we have total of all three components. And in this part we have the lifetime, and in this we have inventory. So we can see that these are the organic, this one organic carbon, this is only table is only for the organic carbon in soil and sediments, that totaling to 1600 gigatons of carbon. Now moving ahead, now we have carbon inventory of ocean. So oceanic carbon inventory holds around 39,000 gigatons of carbon, and in this more than 90% is being contributed by bicarbonate ion, as we can see in this. The remaining oceanic carbon inventory consists of carbonate ions, dissolved carbon dioxide, dissolved organic carbon, and marine biomass, which has very less contribution, as we can see that it is less than 10. So all this totals up to 39,000, and we can see that this is the highest carbon inventory out of the atmosphere and the and in soil and sediments. So the carbon inventory of ocean contributes the highest amount of carbon uh, in gigatons per carbon. So now moving ahead, now we have discussed about all the carbon inventories. Now we will discuss about carbon cycle. So as discussed earlier, the carbon inventories are present in the atmosphere, biosphere, lithosphere, and ocean. And all these carbon inventories are linked by a complex set of natural, chemical, biological processes. And this complex cycle is known as the carbon cycle. So now talking about the carbon capture. So this is the first process of the CCUS technology. So basically carbon capture is technology for trapping the carbon dioxide emissions that are released during power generation or other industrial processes before the emissions enter the atmosphere. So there are basically three approaches of to carbon capture or carbon dioxide capture. First involves the process modification. The second includes the post-process capture, and the third is the direct capture. Now talking about the process modification. So in this, carbon dioxide can be captured as pure carbon dioxide stream, or we can modify a process to generate such a pure carbon dioxide stream. So this process modification is used in oxy-fueling in the power generation plant. So as you can see in this flow diagram, first we have the fuel, air, and other raw materials. So first they undergo pre-processing, in which N2 gets separated out. Then the flue gas passes into the power plant, or it undergoes some industrial process in which the carbon dioxide gets separated from other process outputs. Now moving ahead, we have the second process, which is the post-process capture. So in this, carbon dioxide can be captured by concentrating the industrial discharge into a pure stream. Example of this post-process capture is that this occurs in the post-combustion separation power plants. So in this flow diagram, we can see that as inputs, we have fuel, air, and other raw materials, which passes into the power plant, or it undergoes some industrial process. And then there are two outputs. First, we get a mixture of nitrogen and carbon dioxide, and other, we get the process output. So the mixture of nitrogen and carbon dioxide undergo a carbon dioxide separation unit, in which both of them get separated, and we get a pure carbon dioxide stream. So the third and the last approach is of direct capture. So in this, carbon dioxide is captured directly from the air into a pure carbon dioxide stream, and this is used during mineralization of the steel slabs. So as we can see that from directly from air, we have separated nitrogen, and we have found the pure carbon dioxide stream. These were the three approaches to carbon dioxide capture. Now let's talk about the various processes that are used in capture during power generation. So there are three processes. First being the post-combustion capture, second is the pre-combustion capture, and third is the oxy-fuel combustion. So talking about the post-combustion capture, so in post-combustion capture, carbon dioxide is removed from the flue gas after combustion at low pressure by using chemical solvents such as amine. And this post-combustion capture process is generally used in power plants. So in this flowchart, as you can see, we have coal, gas, biomass, and then we have air. So both of them undergo power and heat, and then it forms flue gases, and then it undergoes a separation unit in which carbon dioxide gets separated after combustion. So in this process, in the power and heat process, combustion occurs, and then we get separated carbon dioxide. Now talking about this process, this is the pre-combustion chamber. In pre-combustion capture, carbon dioxide is removed before combustion process. As the name only indicates that it is pre-combustion, so we get to know that the carbon dioxide gets separated before the combustion process. The fossil fuel reacts with air, that too specifically speaking oxygen, to form carbon dioxide and hydrogen, and this hydrogen can later be used as a fuel. So this pre-combustion capture process is mainly used in industries. So in this flow diagram, we can see that first we have coal, gas, and biomass, and then we have air and oxygen stream. So this undergoes the gasification process. Then we have the separator unit in which we can see that before combustion only carbon dioxide gets separated, and then the H2, and after gasification we have basically a mixture of carbon dioxide and hydrogen, also known as the syngas. So when it undergoes the separation process, carbon dioxide can get separated, and the H2 fuel gets separated, which can be then used, which undergoes combustion and can be used as a fuel. Now talking about the third method of capture from power generation is the oxy-fuel combustion. So in this oxy-fuel combustion, fossil fuel is directly combusted in oxygen, and this process is used in welding of steel and power and other metals. So as we can see, we have coal, gas, and biomass, and then we directly combust this mixture in oxygen, and see here is the combustion process, and we directly get carbon dioxide. So these were the three methods of capture from power generation. So let's just quickly summarize the advantages and disadvantages of capture options. We have three options: pre-combustion, post-combustion, oxy-fuel combustion. So in pre-combustion, the advantages are that low energy requirements for the capture process, and it is a fully developed technology, and it is already commercially deployed at the required scale in various industries. Disadvantage is that the temperature and the efficiency, there are some issues related to temperature and efficiency because of the hydrogen-rich gas turbine fuel. Now talking about the post-combustion, in this, it is also a fully developed technology, and it is already commercially deployed at the required scale in other industries. And in this, opportunity for retrofit is also existing. But the disadvantage is that there is the parasitic power is very high, and there is requirement for solvent regeneration. And the major disadvantage is that the carbon dioxide impact is very low efficiency, and high capital and operating costs are required for the current absorption system. Last process was that of oxy-fuel combustion. In this, the advantages are that there is mature air separation technologies available, and the very high carbon dioxide simplifies capture process. So this means that there is high efficiency of carbon dioxide, and therefore it simplifies the capture process. But the disadvantage is that it is very costly and energy intensive air separation step, and significant plant impact makes retrofit unattractive, which means that we cannot use retrofit methods for oxy-fuel combustion. Now the capture, the first stage, that was of carbon capture, is completed. Now we are moving on to the second stage, that is transportation. So there are two main options for the large-scale transportation of carbon dioxide. They can be either via pipeline or via ship. So talking about pipelines, as we know that pipelines are generally the cheapest way of transporting any substance, and in this case, it is the cheapest way of transporting carbon dioxide in large quantities. And transport by pipeline has been practiced for many years, and it is developed at a very large scale. There is an extensive onshore carbon dioxide pipeline network in North America with a combined length of more than 8,000 kilometers. Now, talking about shipping, that is the second mode of transport. Large-scale transportation of carbon dioxide by ship has not yet been demonstrated. Currently, carbon dioxide is shipped in small quantities for use in the food and beverage industry using shipping. Now, talking about the third step, that is the carbon storage. This is a very important step in CCUS. So there are basically carbon storage can be used for in geological storage, and we have oceanic storage, and we have storage by mineral carbonation. So talking about geological storage, we have that storage in formation in containing non-potable water. This means carbon can be stored either in saline aquifers or it can be stored in oil and gas reservoirs. We can use both depleted and producing oil and gas reservoirs. So carbon dioxide injection into the oil reservoirs is widely used as an enhanced oil recovery technique. This technique is particularly used in the Permian Basin oil fields in USA. An injection into depleted gas aquifers has also been demonstrated in the Gaz de France K12B field in the North Sea. And saline aquifer storage has been demonstrated in Statoil hydro-operated Sleipner field in the North Sea. So as we can see that geological storage is a very convenient form of storage, and we can already see that all the three methods, that is oil reservoirs, depleted gas aquifers, as well as saline aquifer storage, has already been demonstrated in various parts of the globe. Now talking about the second storage method, this is oceanic storage. As you can see in this diagram, this is the power station where CO2 capture process is happening, and then we can see that via pipelines we are transporting it to the various storage facilities. Here we have unminable coal beds, here we have the deep saline aquifers, here we have depleted oil or gas reservoirs, and here we have the oceanic storage. So talking about the oceanic storage, so long-term storage by direct dissolution into deep waters could be achieved by venting out gaseous carbon dioxide or supercritical fluid at sufficient depth so that it is ensured that the dispersal of rising buoyant plume is achieved before it reaches the surface water. And carbon dioxide can also be stored as in a lake, as a lake of supercritical fluid is injected below the depth at which it becomes negatively bound in seawater, which means that it can be stored as supercritical fluid at a depth below 3000 meter below the sea level. Now talking about the next form of storage, that is storage by mineral carbonation. So in this process, there is formation of stable carbonates by the reaction of carbon dioxide with naturally occurring oxides or silicates of magnesium, iron, and calcium. So igneous silicates, which may be such as olivine, serpentine, or wollastonite, they are potential feedstocks for mineral carbonation. So alkaline waste from this igneous silicates was for large scale applications. Now talking about the small scale applications, here we have alkaline waste from industrial process such as ash from waste incineration and coal combustion. They are suitable for mineral carbonation at smaller scale. So we have talked about mineral carbonation at larger scale as well as mineral carbonation at smaller scale. So in this diagram, as we can see, this is power plant which is generating the carbon dioxide. Then carbon dioxide is being transported via pipeline, and then it is being stored in mineral carbonation plant. And the minerals may be either olivine, serpentine, or wollastonite. Now, here is a table of the capture-ready power projects which are currently in development. So here we have just discussed four major capture-ready power plants. First one is the Karsto, that is in Norway. Second one is Rotterdam's Eon, Netherlands. Third one is the Kingsnorth Eon, UK. Last one is the Saline Sonish, Italy. So these are the project descriptions, that it tells us whether the plant is gas fired or coal fired. Then it tells us what is the megawatt capacity. Then it also tells us how much in metric ton carbon dioxide is generated per year. And then it tells us about that. And as you can see that all these plants are post combustion capture ready power plants. So now we are moving on to the approaches to zero emission power generation. So in addition to the options that were already discussed, like the post-combustion process, the pre-combustion process, the oxy-fuel process, which essentially apply capture technology to conventional power generation systems that, as we have already discussed, that they are only for the power generation systems. Now, we have that a number of alternative concepts have been proposed to achieve net zero emission power, that is ZEP generation, using various novel components. So in this presentation, we'll basically discuss two concepts. First one is the ASAP concept, second is the ZEP concept. Now moving forward, first let us discuss the AZEP concept and the systematic flow diagram. So the Advanced Zero Emission Power Plant. This is short form for AZEP. AZEP stands for Advanced Zero Emission Power Plant concept. This was proposed by Norsk Hydro in the year 2002. So in this concept, there is a Brayton cycle gas turbine. So we can see this is a Brayton cycle gas turbine in which oxy-fueled combustion of natural gas is achieved in a mixed conducting medium MCM membrane reactor. So here is the MCM reactor in which what happens is that there is oxy-fueled combustion. Here you can see these are the combustors. So uh, fueled combustion of natural gas is achieved in this, and then it passes on to the Brayton gas turbine, and then carbon dioxide, everything is generated here. As we can see that in the end, carbon dioxide, we get a pure stream of carbon dioxide, and we get other products as well, such as H2O, H2O and the like this oxygen depleted air. These are the side products. So in this ASAP, we can achieve high efficiency by using an HRSG plus steam turbine cycle. Here is the steam turbine cycle, HRSGS plus steam turbine. This is used for increasing the efficiency of the AZDP power plant. So now let's move on to the second concept, that is of the ZEC concept. This is the flow diagram. So ZEC stands for the Zero Emission Coal Concept. It was proposed by Los Alamos National Laboratory, and it was further developed by the Zero Emission Coal Alliance, that is ZECA. So the Z concept integrates the following advanced technologies. These are the technologies. First is that the coal gasification for hydrogen production and chemical looping for removal of carbon dioxide from syngas. So this is the basic schematic flow diagram. So first we can see that coal undergoes gasification, and then other processes such as gas cleanup, carbonation, hydrogen polishing, calcination. Again, we have gas cleanup over here. Then we have a fuel cell, and finally at the end we achieve carbon dioxide compression, and then we get carbon dioxide as a pure stream. So these were basically the two net zero emission concepts. First one was AZEP, and this is the ZEC. Now this is the last step of the CCUS process. First one was capture, second one was the transport to the storage sites, and we are storage, and then we are utilizing the stored carbon dioxide. So here we can see that this is the captured carbon dioxide. So it can be used in various industries. If we say that this is the biological conversion, extractant, mineralization, chemicals, refrigerant, miscellaneous, inerting agent, fire suppression, plastics, enhanced fuel recovery, and food products. So as we can see that so many different applications of the captured carbon dioxide can be achieved. And these are the various examples. These were the industries, and these are the various examples of carbon utilization of the captured carbon dioxide. So now coming towards the end of the presentation, let us discuss some policies before ending the presentation. We are on in this PVT, we are only discussing a few countries, like we have only 4 countries. There are even other countries. So let us discuss first. Let's discuss about the United States. So in 2021, it is very recently, the US passed the Infrastructure Investment and Jobs Act, that is the IIJA, which provides approximately 12 billion USD for the CCUS value chain, and it will be provided up till the year 2026. That is 3 years from now. So this act was implemented in United States. Now talking about the United Kingdom. So under the Spring Budget 2023, GBP 20 billion in funding was announced for the early development of CCS projects, particularly on the east coast and in the northwest of England and the northwest. So 20 billion of Great Britain pound was funded for the development of CCS projects in particularly these three locations, that is the east coast, the northwest of England, and in North Wales. Now, in European Union, in March 2023, the European Commission introduced the Net Zero Industry Act, which identifies CCUS as a strategic net zero technology for which scaling up of manufacturing capacity is critical to reaching the European Union's climate goals. And in Canada, as part of its budget 2023, Canada proposed an expansion and additional design details for its investment tax credit for CCUS projects. So, these were the basic major policies that have been implemented in different parts of the world for the development of CCUS projects so as to achieve the climate goals and net zero emissions. Now, so that was all from my side. I hope that I have presented all the topics on CCUS. Thank you.